The latest research results suggest that something dramatic once took place in the solar system millions of years ago. A foreign star collided with our home world and came closer to our central star than the Voyager probes are today. Indeed, the consequences of the stellar visitor may still be felt. After all, it not only drastically changed the orbits of the trans-Neptunian objects but also significantly influenced the moons of the large gas planets. But how did the stellar passage unfold in detail? Why did it have such a major impact on the structure of the solar system? And what lessons can experts learn from this unique encounter? Farther and farther, the two NASA probes Voyager 1 and Voyager 2 venture into the question of the most remote outposts of humanity. There is no getting around the world-famous sister probes, and it's no wonder why. Although the identical spacecraft only set out into space in 1977 to gather new information about the outer planets of the solar system, they have now ventured into interstellar space. Expressed in numbers, this means that Voyager 1 and 2 have now put an incredible distance of 24.6 and 20.6 billion kilometers, respectively, between themselves and the Sun. While the Voyager probes are giving us unprecedented insight into uncharted cosmic worlds, we should not forget that it also works the other way around. In fact, a new research study suggests the astonishing conclusion that an alien star once entered the solar system, significantly undercutting the distance that now exists between our host star and the Voyager probes. But what is it all about, and how could this stellar passage help us solve some tantalizing mysteries of our home system? To understand this, we have to venture a little way into the world of the moons of the solar system. We must bear in mind that these sometimes exhibit completely contradictory characteristics. On one hand, there are the satellites that behave as one would expect, such as Earth's moon, which orbits our blue home planet in a prograde direction, meaning it follows the Earth's rotation. However, this scheme does not apply to all satellites in the solar system. Outer planetary worlds such as Jupiter and Saturn have a strikingly large number of companions that, simply put, move in the wrong direction. The technical term for this is retrograde orbit, where the moons orbit against the direction of rotation of their planets, usually on highly inclined elliptical paths. The contrasting moon patterns are by no means evenly balanced, quite the opposite. In the case of Jupiter, experts count 71 retrograde satellites, while the mighty gas giant simultaneously has only 16 prograde satellites. In the Saturn system, the differences are even more pronounced, with a ratio of retrograde to prograde moons of 100 to 22. Where do the retrograde moons come from? In a nutshell, experts have long assumed that retrograde moons are, to put it casually, newcomers. Unlike their prograde counterparts, these satellites did not form together with their planet but rather in a completely different part of the solar system. Scientists locate the formation region of these satellites in the distant Kuiper belt, a ring-shaped area beyond the orbit of Neptune. Researchers believe this is where the roots of most comets with medium periods lie. Objects that later became retrograde moons may have been ejected from the Kuiper belt and subsequently fell into the gravitational influence of the large gas planets. For a long time, astronomers pointed to the Jovian migration theory, which posits that Jupiter initially formed farther out and then gradually migrated inward. This migration was only reversed by the formation of Saturn, which ultimately established Jupiter in its present orbit. The preceding passage did not resemble a leisurely stroll, but rather, as the saying goes, a bull in a china shop. As Jupiter swept through the early solar system like an oversized wrecking ball, it triggered a mass collision of countless planetesimals, planet seeds. In this way, the inner solar system was practically swept clean, creating space for the formation of small gas-poor rocky planets. Without Jupiter's migration, Earth and the other terrestrial planets might not have existed. Retrograde moons are thought to be a relic of this violent excursion. However, this theory has a small but crucial catch: it cannot explain all the properties of the moons in question. For this reason, a team led by Suzanne Pfalzner from the Jülich Research Center, along with colleagues from Leiden University, looked for alternative explanations. They focused on the close flyby of a foreign star, a radiant visit with consequences. Our solar system does not end with Neptune. Researchers now know of several thousand celestial bodies in the trans-Neptunian realm, with tens of thousands of bodies over 100 kilometers in diameter. Surprisingly, many trans-Neptunian objects move in eccentric orbits inclined to the common orbital plane of the solar system planets. To understand the reasons for these orbital characteristics, Falsner and her colleagues, Anthony Gann and Simon Porteges-Swart from Leiden University, conducted over 3,000 computer simulations. The results, published in Nature Astronomy and the Astrophysical Journal Letters, concluded that the strange orbits of trans-Neptunian objects may be due to the influence of a foreign star. This could even explain the orbits of very distant objects, like the dwarf planet Sedna, discovered in 2003. Sedna orbits the Sun on a highly elliptical path, reaching as far as 17 astronomical units from our star. According to the team's explanation, a star slightly lighter than the Sun, around 0.8 solar masses, passed at a 70 degrees angle to the planetary plane and came significantly closer to the Sun than the Voyager probes currently are. While the Voyager probes are now 24.6 and 20.6 billion kilometers from the Sun, this stellar visitor may have approached as close as 16.5 billion kilometers, roughly 110 astronomical units or a little less than 4 times the distance between Neptune and the Sun. This encounter would have caused a series of drastic gravitational disturbances. In the model, these disturbances flung many objects in the outer solar system farther outward or even out of the solar system entirely. At the same time, some trans-Neptunian objects were catapulted inward. Although 7% may not sound like much at first, this percentage represents up to 10 million objects 100 kilometers in size or up to 10,000 objects larger than 1,000 kilometers. Some of these objects, the team hypothesizes, were captured gravitationally as moons by the outer gas planets Jupiter, Saturn, Uranus, and Neptune. The researchers' simulations could even reproduce the ratio of prograde to retrograde moons in the Jupiter region, showing that the probability of objects entering retrograde orbits was about 30 times higher than prograde orbits. The irregular moons are not only characterized by their mostly retrograde orbits but also by the larger inclinations, eccentricities, and distances of their paths. Scientists consider the simplicity of their model one of its greatest strengths. A single cause appears to explain many of the solar system's mysteries. Furthermore, it's even conceivable that the solar system might not have existed in its current form without the close flyby of a neighboring star. Another intriguing hypothesis suggests that around 4 billion years ago, a star the size of the Sun passed close to the young solar system, tearing away much of the primordial cloud and reducing the mass of the Kuiper Belt region to around 1% of its original mass. What was nearly a catastrophe in the distant past may now offer a plausible explanation for the trajectories of many trans-Neptunian objects and the sparse population of the Kuiper Belt. And if you never want to miss a video from our channel again, there's no more plausible approach than clicking the subscribe button now. We'd love for you to join our community so you can stay up to date. We'll see you soon.